Thank you. Thank you all for joining us today. It's great to be here with you. I'm excited to join the team and teach the signal processing course starting in March. I've been teaching engineering for about 20 years, teaching signal processing and usually communication systems. Also have taught analog circuits and digital circuits. In addition to teaching, I've done research in the area of signals related to global navigation satellite systems. So specifically GPS signals, but it's applicable to other GNSS systems across the world. How do we acquire navigation signals from satellites, but also how can we navigate in challenging environments, say if we're being spoofed, jammed, or if we have weak signals from space. So I'd like to introduce the signal processing course that we'll be teaching starting in March. And we'll start with a review of signals and systems, but we are going to focus mostly in this course on digital signal processing, or sometimes we refer to it as discrete time signal processing. We'll talk about what we mean by the difference of those two things. And one of the interesting things about signal processing, we take a perspective a lot from the frequency domain. So what are the frequency content of the signals that we're trying to investigate or adjust or filter? And so you may have heard of the Fourier transform. I've seen that in your previous studies. So we'll review how the Fourier transform will allow us to look at signals in terms of their individual frequency components, say a complex exponential or sines and cosines. But we'll introduce the discrete time Fourier transform. So how do we investigate the frequency content of discrete time signals? We're all aware that we can create signals from its samples, the original signals. So as you listen to music each day, we're listening to digital music, samples of the music, but we're convert them to the analog domain and we can actually reconstruct the signal. So it's pretty neat that we can take samples of a signal and reconstruct the signal. The figure on the lower left is an example of a signal with multiple frequency components. And if we sample fast enough, we can accurately represent that signal. But there's also an example if we're not sampling fast enough, how that signal is an alias and it actually represents something else. So after our review of signals and systems introducing the discrete time Fourier transform, we'll talk a lot about sampling and reconstruction and some of the effects that sampling in the time domain, what that does in the frequency domain in terms of the Fourier transform. We'll see some periodicity there. We'll also introduce another technique for a different representation of signals, and that's the Z transform. It's you may think of it as the Laplace transform for continuous time signals is equivalent to the Z transform for discrete time signals. We'll then spend some time thinking about investigating systems from a transform domain perspective. So what do these systems and signals look like if we look at them in the frequency domain or the Z domain, for example? It allows us to investigate systems. We want to create signal processing systems that are stable. Also, if we're operating these in real time, we want to create signal processing systems that are causal, where they don't depend on future inputs. So we'll look at, from a transformer domain perspective, what does it mean to create a stable and causal system? We also look at the frequency response of these systems. What is it, which is in general a complex number. So we'll look at the magnitude response and the phase response. And we'll see that if we are processing signals and we want every single frequency component to be delayed by the same amount of time, we want a linear phase system. So we'll talk about what that means as well. And then a big portion of the course is about filter design. So as we process signals, we may want to adjust their frequency content or their spectrum. And so we'll introduce how to design digital filters. And we'll review some of the classical analog filter design techniques. And we'll show how we can transform those into discrete time or digital filters, including low pass filters if we want to smooth signals out to get rid of high frequency noise, or other kind of filters such as band pass, band stop filters, or high pass filters. We'll spend a little bit of time talking about implementation. So if we want to implement these systems in a computer or in a digital system, what does that mean, and how can we optimize it to implement it fast and efficiently? We wrap up the course by talking about spectral analysis. one aspect of signal processing is investigating the frequency content of signals. So we'll introduce the discrete Fourier transform, which allows us to look at signals that are discrete in time, but also discrete in frequency, so we can actually process them on a computer and investigate their spectrum. And we'll look at efficient ways to do that, such as the fast Fourier transform. If you guys head to the next slide. This is my last slide just to introduce. We go through a foundation of signal processing in this course, but there's numerous applications in this field. And so after this course, I feel like students will be well prepared to head off into any of these domains that apply and use signal processing. For example, wired and wireless communications. A lot of communications these days now involve software-defined radios, which are processing these communication signals. Streaming multimedia applications, audio and video, even in terms of audio, even computer synthesized music is processing these signals and creating sounds on the computer. Lots of efforts now in speech processing. How do we reduce the amount of processing required or storage required for speech? Geophysical exploration. So if you have signals with volcanic activity or earthquake, seismic activity, how can we process those signals effectively to reduce the noise, for example? There's many radar, sonar applications if we're trying to find things out there with signals. And then our course focuses on usually one-dimensional signals with respect to time, but you can also think of images as a two-dimensional signal. So a huge field in medical imaging. So these are many applications of signal processing that I think a great foundation in our signal processing course, and indeed this whole online MEng program will prepare you to venture out to and have some fun with these applications. So I look forward to hopefully seeing many of you online in a future course in our program.
I'm very excited to talk a bit about the class that I'm offering for the 9 courses here. This is applied natural language processing. So what you should expect on applied natural language processing is the following breakdown of information. First of all, natural language processing is how we communicate. So, we want to start off with what's the basis of human language. So you'll learn formal elements such as natural language, grammars, the basics of computational linguistics. And then there you'll start getting exposed to what are some of the basic and standard techniques of just natural language processing. Some of you may already know these things like tokenization, which is what's the smallest piece of data that you can capture that actually has some information. And a token typically may be a word, or it could even be just a syllabus, or it could just be a part of speech, or it could just be a sound that is made that you can get some information out of. Other things like syntactic parsing. Well, if you think back to, your days in grade schools where you're trying to figure out, how to diagram a sentence, here's the noun, here's the verb, etc. That's very important. How do you make that computational? And then the last piece, which is truly for me, what I think is the heart of natural language processing and why we're making strides now, semantic understanding. What does that mean? Meaning, when you get some information, when somebody says something to you, what does it really mean? How can we do that with a computer also? Now, of course, with all that being said, what are the challenges? What makes this problem really hard? It actually doesn't take much to think about. So let me just go back to semantic understanding again. Let me give you the sense called the rock ate. So you have a rock and it's eating. Rock is, an inanimate object. But if you look at it syntactically, just the way the sentence formed, it's valid. You have the rock ate. Very simple. Well, this tells us something. What if we were talking about the rock as some of you may know as Dwayne Johnson, right? So now that makes sense. That actually has meaning. These are some of the challenges we have to deal with. What's the ambiguity? That's a classic case of ambiguity. What's the context of, what you're listening to? You have other things like, what's the user intention? For us to communicate each other, there must be some intention going on. You're here for a purpose. I'm here to help you satisfy that purpose. And then there's a lot of really interesting things beyond that we humans take for granted many times. If you look at, there's things like garden pathing. It's like telling somebody a story, but deliberately leading them down the wrong path and then surprising them with a change at the end. Sarcasm, metaphors, poetry, bias. These are all the elements that makes this problem hard, but also makes it really cool of why we're interested in AI. Next slide, please. So from all that, we're going to look at the different tools for natural language processing. So not just from the basic structured tools that I just talked about, the tokenization stuff, but what are the other things that you need? You might have things which are called ontological tools. This is how knowledge and meaning is organized. You have just even simple thesaurus. Why two words mean the same thing. So you have things like entity extraction, entity resolution. Some may have even heard of things called n-grams, which is trying to capture patterns, how words fit together. And then, of course, what's the state of the art? Large language models. I don't think I need to say too much to this group, but we will be looking at large language models, chatbots, prompt engineering, fine-tuning, all the things that are just really exciting, but also at the same time, one of the most important elements of this is, what are the limitations? This is what we hope to teach you from this class. And then lastly, fitting with the whole point of our entire computer engineering program, online program here for this Master of Engineering, is the applications, how you go about identifying the problem, how do you go about coming up with the solution, how do you develop an answer that's end to end, and then all the elements of validation and assessing, is it doing the right thing? And these want to be application driven. So you could have applications from, say, the financial sector. Hey, if I have news, sector, annual reports, all these assessments, what can I do with all that information? This is a natural language problem. What can this lead us to? So in a nutshell, this is what the applied natural language processing has been aiming to do.
Before I tell you about the graduate level embedded systems course, let me first just define what embedded systems are. That might be a new term. So embedded systems can generally be defined as processor-based systems that perform dedicated functions. Because of this, embedded systems can be highly optimized for their functionality. Some common optimization constraints include size, weight, power, performance, and cost. And that's why the title of the slide says embedded systems doing a lot with a little, because designing against optimization constraints like these can make for some pretty exciting design challenges. So the last, I think, primary feature of an embedded system, and this is one that I personally really enjoy, is that embedded systems interact with the physical world through sensors and actuators. So on the left here, you see Dexter, and this is one of the robots I've used in the undergraduate course here, as a system built entirely of actuators. But Dexter's holding up one of the sensing systems you'll build in this course. And this is a high-performance analog sensing system built with a specific class of processor called a microcontroller. We'll talk a lot about microcontrollers in this course. And this project is a sample of what the course is all about. This is a course on microcontroller-based embedded system design with an emphasis on sensing and processing in intelligent systems. And next slide. Yeah, thank you. So here are some of the topics we're going to cover in this course. And you may have seen some of these before in an undergraduate course. If not, that's fine too. An undergraduate course in embedded systems is certainly not a prerequisite for this course. But in our graduate level course, we're going to cover these topics in more in depth, or probably more correctly from the ground up. Because our course begins where modern computing begins, with the transistor. And the course works its way up through the architecture of embedded systems, and then across the details of how our design tools work in concert with the architecture to help us realize our design objectives. So we'll then take multiple passes at sort of the core functionality of these microcontrollers, and that's data input, processing, and output. And we're going to explore this first with basic software and hardware techniques, but we'll revisit these capabilities a few more times as the course progresses with increasingly advanced hardware and software techniques. So I mentioned that an undergraduate embedded systems course is not a prerequisite, but you will absolutely want a solid foundation in C programming for this course, and at least some exposure to basic analog and digital electronics before taking the course. This is very much a hands-on course. We have multiple programming and hardware design projects that you will do on your desk. We get into these projects in the first week, and the course builds on itself week by week. So it's really important to start the course confident in your C programming skills and comfortable with these basic electronics concepts. So what should you expect from this course, right? That's the question I'm trying to answer for you here. And that is that at the end of this course, you will be able to design, develop, prototype, test, and build embedded systems that can sense in and interact with the physical world. So when you get to the end of the course, my question for you will be, what will you create?
So yeah, I'll be teaching two courses. I'll be doing the FPGA architecture and algorithms course as well as machine vision. But specifically for the FPGA architecture course, this is basically going to be an intersection of FPGAs, algorithms, and embedded systems. So we're going to be learning advanced digital design techniques, such as high-speed digital design, timing analysis and closure, specific hardware optimizations for the FPGA, as well as SoCs, system on chip. And then we'll be also looking at verification and validation, as these are crucial things in industry specifically as well. I'll be doing this all with a hands-on learning approach. So you'll actually have physical hardware on your desk that we'll be playing with every single week. We'll be doing toy problems that will help us build towards our final project, which will be culminating in the final module. But we'll be using the Xilinx design tools, Vivado and Vitis. These are industry standards, so should set you up pretty well to be using FPGAs and embedded systems in the real world. We'll be looking at hardware description language, and so we'll specifically be using Verilog, and then you'll be programming on the Zinc system on chip. So there's lots of applications for FPGAs in all industries, basically, but specifically some of the ones that are hot, want you to say hot right now, include autonomous driving, radar systems, high throughput, high speed video streaming, parallel computing, music and audio processing, as well as wearable sensors. So we can't actually take a deep dive into all of these, but they all have the same fundamental principles of we have signals coming in, we do some processing on hardware, and then we have signals coming out. So we'll be sort of touching on aspects of every industry in the course in all of our little toy problems as we go through the term. But it's going to be really fun. It's all going to be project-based and real-world applications. So you should definitely join the program. It'll be a good time.
So for the machine vision course, machine vision is in all of our lives right now. We use it. Our systems are using it for facial recognition, augmented reality, character recognition, self-driving cars, anything in healthcare with autonomous delivery of medicine, as well as diagnostics, and then super resolution imaging, and the list goes on. But at a high level, a machine vision system has some sort of data input. We sense that input somehow, we interpret that input, and then we have an output, some sort of decision. So if you go to the next slide, in the course, we're basically going to be we're going to be using tools that we will also be touched on in all other aspects of this curriculum. So we'll be using machine learning. We'll be looking at computer vision algorithms. We'll be actually implementing a lot of this stuff on hardware and embedded systems. And then there's the signal processing aspect of it. And it all sort of comes together as machine vision. So more specifically, we're going to be learning about AI vision methods and techniques, 2D and 3D image processing algorithms for stereo vision, as well as hardware optimizations when you actually perform these algorithms on hardware, as opposed to doing it in software where things are performed sequentially. We're also going to be looking at machine learning models for specifically for vision and the real-time hardware and high-speed design considerations that go into these machine vision systems. And the course is all it's a hands-on learning approach. So we're going to be using hardware on your desk throughout the course and doing hands-on labs where we're going to be exploring these algorithms. And then by the end of the course, you will have built your own real-time machine vision system on the Zybo hardware board. And we'll also be looking more into programmable hardware. So we'll be getting into some of the FPGA work that you'll look at in one of the other courses, as well as some of the embedded systems topics. So it should be really fun. And by the end of it, you will have a working system, which will be pretty cool.
And I'll be teaching the distributed computing class part of this program. So most of the other classes in the program, you'll be working with individual processors. So that may be something like machine learning or deep learning or signal processing that you're doing on your own PC or laptop. It may be the FPGA class or the embedded systems class where you're working with dedicated embedded hardware that's sitting on your desk. And in this class, we'll be looking at how do you make a bigger system out of these. So we're thinking broadly in this program about intelligent systems. So we'd like to know how can we scale to a larger network. So this class is really looking at how do we take these individual computing elements and expand them to a larger network. You may have heard about distributed computing. It's all around us in applications like cloud storage. You've heard of Google Drive, Dropbox, Amazon Web Services. Media streaming, Netflix, Amazon Prime, Spotify, Zoom, Coursera, this particular webinar are all using distributed computing to get content to you. Remote sensing is a big area. It's something we think about at Thayer and some of the research work that we do. Internet of Things, another big topic. Distributed learning, we'll be thinking about how we do machine learning and deep learning, but do that close to the source of the data. You could think about healthcare applications where maybe there are privacy concerns where you'd like to do your learning and distill down the data you're trying to get out of, say, medical records without having a HIPAA violation. And then swarm robotics, an area that I'm really interested in as my research is more focused in the robotics side of things. So typically, as I mentioned, we're developing for a single processor, and this is really easy to develop. It's easy to test. It's easy to deploy, but this can be slow. You're limited to one processor. It's failure prone, and it's geographically constrained. Imagine if you wanted to stream Netflix and you had to connect via your network connection to Netflix, say in California, from wherever you are in the world. That wouldn't really be sustainable. It would be hard to support a large user base. So the idea in distributed systems, like the lower graphic on the slide here, is to make the client think that they're talking or their computer is networking with a single device, whereas really behind the scenes, they're working with a number of different processors that have to coordinate together. So this allows concurrent operation. It allows the actual servers to be proximal to the data and to the end users, but these are more complicated systems to develop. They're more corner and edge cases, things that can go wrong. They're harder to test, they're harder to deploy, and that's why we have this course. So we can learn about some of the intricacies of making this happen. Next slide, please. So in this course, we're going to learn really from a systems engineering perspective, how we might design and implement a distributed system. We'll learn fundamentals of networking. This may be something that you're familiar with now, or it may be brand new to you. We'll think about hardware protocol levels and the application layer of how we actually get computers or processors to talk to each other when there's not shared memory. I'll look at the building blocks of what we call concurrency, which is how we make things happen at the same time. So threading, again, is something you may or may not have had experience with. Remote procedure calls will probably be new, and we'll talk about microservices and other building blocks that we need to make a distributed system. And then finally, we'll study some of the seminal implementations that are out there, both in academia and industry, to learn about the algorithms we can use for consistency to make sure our applications are fault tolerant, and security is a real big topic in distributed systems. So just as Kendall mentioned for the machine vision class, this will be an applied learning class. It'll probably be more heavy on the programming than on the hardware. But we will be having frequent programming labs and assignments. We'll have case studies, as I mentioned, from both industry and academia. And our goal at the end of the course is to be able to have an Internet of Things implementation and to explore federated learning, which I mentioned before. If we're trying to do deep learning, we might want to, instead of learning everything on our computer on our one dedicated GPU, we might want to spread our learning out among the sources of data and then pull back together the insights that we get from that into one unified model.
Webinar. So my name is Professor Dartmouth, and I will be teaching the Smart Sensors course. Now, the idea with this course is we will take the skills that you develop throughout the MEng program and then apply them to building your very own custom smart sensor. So the question is, what is a smart sensor? Well, looking at this slide, we can see different applications of smart sensors. In precision agriculture, for instance, smart sensors can sense temperature, humidity, wind speed, and then use this data to forecast frost, for example, to avoid crop damage. We can see smart sensors in industrial settings where they measure the vibration of factory machines, and then from this vibration data, the smart sensors can determine the optimal time to perform preventative maintenance. And in the consumer health realm, Smart sensors can be used to detect sleep apnea. They can track mental health states. They can even measure blood pressure. So smart sensors are typically implemented as embedded systems, and these systems have a few hallmark features. One, they are physically small. They are battery operated, which means we are limited in the amount of computation we can do. We're limited in the amount of communication we can do also. And these sensors, in addition, have latency restrictions. That means that they must act and respond more or less in real time to the physical signals that they are sensing. And then finally, because the sensor is out in the unconstrained real-world environment, we need to deal with the fact that the signal that it senses, the data that it collects, might not always be of the highest quality. So we need to figure out how to deal with that. So next slide. So what you will learn in this course then is to learn how to overcome all of the constraints of a low resource embedded system. We will do this learning within the context of a custom mobile device for measuring the ECG heart signal. So that's what is shown on this slide. On the left-hand side, you've got the device that we're going to be building. In the middle, you've got the signal, the ECG signal that we will be sensing. And then on the right-hand side is a depiction of the sort of interesting signal processing, nonlinear processing, even deep learning, deep inference that we'll be applying to the signal on the sensor in order to make interesting deductions from the data that we sense. So we're going to build this device from the ground up, and then all of the lessons that you learn while you're building this device can be broadly applied to all these other smart sensor scenarios that I touched on.
Yeah, so I'm just going to tell you a little bit about one of these courses that you would take as part of this degree program that I'm going to be teaching. This is a course in deep learning, which is a topic that a lot of us have heard, but might not necessarily understand the nuances of or what exactly that means. Deep learning is really the science of deriving meaning from really large or complicated data sets. So it's this field of data science where we're concerned with what can we do regarding specifically using a particular kind of neural network, that is a neural network with many layers in between its input and its output, to try to obtain some kind of an insight into what that data represents. So that could look like, for example, predicting what the future of a signal might be if you have data that is a signal through time, or producing new outputs that would fit naturally into the training data set, things like that. So we'll talk a little bit more about the specifics of that. From a very big overview of the course, the idea here is that we want to provide for you a balance of theory and practice. So what that means is that students who are coming through this course are going to become familiar both with the science, that is the underlying knowledge that makes deep learning work, and also the ability to put it to work for themselves, that is to actually do these hands-on projects using Python in order to actually use deep learning for their own purposes. So we're really targeting kind of a holistic approach to that topic. So you're going to walk away with that balance, and you're also going to be equipped with everything you would need to know after this course to train models on your own data sets and actually use machine learning and deep learning in ways that are not just kind of out of the box from a third party. So just a few topics that would be covered in this course, that are going to be covered in this course. First of all, the fundamentals of deep learning. This is really that science, that fundamental science of what is it that actually makes this tick? How does this work on a numerical level? What's going on under the hood? And then talking about several structures or architectures for neural networks. So how can we actually articulate a particular neural network that is suited for structure in data, right? So intuitively, most of us are aware that like sometimes data isn't just a random assortment of numbers, but it instead has a structure. Like, for example, language has a sequence. I can't use words in some random order. They have to be in a particular order. How can we embed knowledge of that structure in a neural network? So that's an important topic. Generative neural networks are something we'll talk about. So we're all really familiar at this point with, for example, ChatGPT. That's a generative neural network that is using a generative AI in order to basically fill in the blank, right? So it's given an input and it's trying to find an output that fits naturally based on its training data. So we're going to talk about those. And then also really important topics in knowledge transfer and distillation. So these are things that are key skills that computer engineers need in order to meet the needs of particular engineering topics. So for example, how do I transfer knowledge from something where I have a lot of training data in order to apply that to something that's related, but where I have very little training data in comparison? Or how do I optimize a model in order to be better suited to a particular task where, for example, maybe my ability to do compute is limited because maybe my application is on a cell phone instead of on a desktop computer. Topics like these that are really important for getting that last mile, bridging the gap from theory to real implementation. Just one particular, we can go to the next slide. One particular project, for example, that we will work on in this class would be training a generative image model from scratch. Right. So like I said, we've all been exposed to some really impressive results in this space. Like, so for example, we might have heard of DALL-E or Stable Diffusion. These are making a big impact in the ability to generate images from prompts, word prompts. But it's actually an entirely different thing to be able to train your own model, right? To be able to equip with the knowledge to build a model like this from scratch on your own data set without needing to license that knowledge or those models from someone else. And that sort of hands-on knowledge really allows us to think about how we might, extend this technology of deep learning into other aspects of our professional lives, other than, what is made available to us in kind of an off-the-shelf way from third parties like OpenAI, for example. So, a lot of these, this is a deep learning, as we all are becoming aware, is a transformative technology, but a lot of people haven't thought about it from your perspective, right? In your particular field, in your particular area of interest, with your particular data sets, right? And so there aren't often tools that are really well suited to exactly the problems you might be interested in. And so that's why it's so important to have the skills to train these things from scratch and to do it in a way that is appropriate for your problem. So one of the big outcomes from this course then is going to be equipping students with knowledge to be able to put modern AI abilities, deep learning, to work for themselves without needing to rely on the walled gardens of third parties. And then also, when it is appropriate to use those third-party tools, it equips us with the knowledge to know when those are appropriate, what they're good for, and where they might not quite meet the needs that we might expect them to, and why. Okay, so that's all I wanted to say about deep learning. Hopefully that gives you kind of a teaser, just enough to be interested in wanting to learn more.